আমাদের সোনাটাও কম্প্যাক্ট হয় এই জন্য। ওকে, লেটস স্টার্ট। Refraction of light. Light travels from one transparent medium to another one. If it travels from one transparent medium to another, then it bends away from the normal drawn at point of incidence. This is our reflecting surface, refracting also, because when light is incident, it can suffer both reflection, refraction, absorption, many things can happen. We have never said that 10% light will be reflected or refracted. Part of it reflected, part refracted, part may be transmitted, part may be absorbed. So suppose on this surface a green light is incident, true for any light of course. This side is vacuum or air, and this is the medium, any medium. At this point, if we draw normal, then it has to go from this medium to the other medium, I mean vacuum to some other medium, then it will bend away from the normal. So refraction will be there, light will not follow the same path, its path will be deviated. This phenomenon of bending of light, don't say bending, bending of light from the normal, it called refraction of light. Just a minute, application should be closed. Yes. So light will go this manner. This is angle of incidence with the normal, the angle it makes, and this is angle of refraction, R. Here I will never be equal to R. I equal to R possible in one case only, that is 0, when it is along the normal. Okay, for refraction also it is possible. So this medium is denser, this one rarer. As it bends away from, bends towards the normal on the other side, that's why it is denser. Situation may be different also. Situation may be like this. This is the normal, light incident here, and normally you produce on the other side, then the light bends away from the normal. It was going this way and now it bends away from the normal. This angle is I, this one R. R is greater than I. This time what will happen? This medium is rarer. Understand? This is the direction of light, refracted light. Refracted light going this way, light incident this way. This is incident day, this is refracted day. Okay, so this is also, say, another medium, say water, and this one air. Can happen this way. This is rarer, that is denser. Snell observed that Snell's law is there, that incident ray, refracted ray, normal lie on the same plane. And number 2, that sin I by sin R, at any point you consider the angle between the incident ray and normal, it's sine, angle between refracted ray and normal, it's sine. This ratio will be a constant. Okay, sin I by sin R equal to constant. This constant will be referring as 1 mu 2. This is refractive index of second medium with respect to first. Okay, refractive index of second medium with respect to the first. You can say this one as relative refractive index also. This can be referred as relative refractive index. So we have considered special case, water here, maybe water alcohol, maybe water oil, maybe you need two medium, one solid, one liquid, can happen. And this is observed that this 1 mu 2 is ratio between speed of light in first by speed of light in second. Light travel with the speed c1 here, c2 here. The ratio between these two is sin A by sin R, which is always a constant, that is speed of light in two medium. Light travels with different speeds in different medium. This 1 mu 2 is for any two medium. I am not specified any one. Okay. But if I take the first medium, always air, taking the first medium, always air, then you can define absolute refractive index. Okay, this will be referred as relative refractive index of second with respect to first. This you can say relative. Okay, then you can define absolute refractive index. Some of you might have done in class 9-10 level also, but do it today before you start geometrical optics with full potential. All these concepts you need to revise. I am going to define absolute refractive index. If the first medium is always air, first medium means where light coming from, and this is medium, any medium, I am not referring water or air, water or alcohol or any other medium. Okay. So light entering from this medium, air, normal is there. It is entering from air to this medium and it goes this manner. It goes this way. O, and this is N. Normal, incident ray, I, R. So 1 mu 2, this time we can write as sin I by sin R, speed in air by speed in medium, isn't it? I need not write this one in the form of 1 mu 2. So what is absolute refractive index? So let me define, if the first medium is air, then the refractive index of the second medium is known as absolute refractive index. If the first medium is here, then refractive index of the second medium is known as absolute refractive index. Clear? And in terms of speed of light, this you can write 1 mu 2 equal to sin A by sin R equal to speed in air by speed in medium. Okay? One thing you have to make clear that this 1 mu 2 has another representation, that is A mu MED, medium. That is sin A by sin R, which is nothing but C air by C medium. Clear? So what we will do, if the first medium remain air, we will not continue with this symbol. We will change this symbol into mu 2 only. Mu 2 or mu of the medium. Air is there, confirm in the first medium. This will be 3 into 10 to the power 8 speed of light, that divided by C2. C2 is the speed of light in the second medium, that is in the medium. Okay? So this is called now absolute refractive index of the second medium. This is absolute refractive index of the second medium, mu 2. Clear? This is absolute refractive index of the second medium. Now, suppose a problem arises this manner. Let me discuss here. Find the speed of light in glass. Given mu g equal to 1.5. Bus. Here it has maximum speed. In glass, speed will be reduced. You have to get it by this. We have given mu g equal to 1.5. So when mu g 1.5 given, this is the absolute refractive index. This absolute refractive index concept will be using to get speed of light in glass. See how I am doing now. This definition will be writing mu g equal to 3 into 10 to the power 8 by Cg. Cg stands for speed in glass. Cg stands for speed in glass. Therefore, Cg will be 3 into 10 to the power 8 by mu g. 3 10 to the power 8 by 3 by 2. This is 2 into 10 to the power 8. So speed of light in glass is reduced and it is given by 2 into 10 to the power 8 meter per second. Clear? Understood? This way you can find. Now, relative refractive index is going to be dominated by this absolute refractive index concept, because we can express the relative refractive index as the ratio of two absolute refractive indices. You don't know light will travel from air to a denser medium always or not. It can travel from any medium to another medium. So to relate the speed of lights in two different medium, I need the concept of absolute refractive index. How? Let me explain that part. So before that, we need to learn principle of reversibility of light. Principle of reversibility of light. All relations I will establish after doing this. What is the principle? If light after traveling, let me write the principle. If light ray after suffering a number of reflections and diffractions had its final path reversed, then it travels the same path in backward direction. If light after suffering a number of reflections and diffractions had its final path reversed, then it travels the same path in backward direction. Okay? If you take a ray of light incident here and get refracted like this in the other medium like this. This is normal, of course. AO, then going this way. This is I, this is R, and what we are doing here additionally, we are fixing a mirror here. In front of this light ray, we are fixing a mirror. Okay? Then we can define at the considering refraction at O, then if this is 1 and this is 2, we can write 1 mu 2 equal to sin I by sin R. Snell's law, the ratio will be a constant. First law, those three lie in the same plane, the reflected ray, the incident ray, the refracted ray and the normal, they will lie in the same plane. Second law is this, sin I by sin R, for any point between these two medium, the ratio will be constant. Any angle, if you are increasing I, then R also will increase. In that case, ratio will be the same. Very interesting proof he did. You can perform the experiment at home to prove this one. Nice proof is there. Just by using plain piece of paper, sending a layer of light and using pins. We are not going to do it now. Now, this is the incident ray and this is refracted ray. What I told, had its final path reversed, 90 degree it is incident, so path of course will be reversed. It will go back this manner. So when you consider taking this one incident ray, this one refracted ray, we get this. Now, when the ray is reversed, then BO is the incident ray, OA is the refracted ray. Okay? OA is the refracted ray. BO the incident ray, OA the refracted ray. Then 2 μ1 will be what? Will be sin R by sin I. Am I correct? This is number 1 and number 2. It is just change. It is coming from here to here, now going back from here to there. 2 μ1 will be sin R by sin I. If you multiply these two relations, what do you observe? Multiplying 1 by 2, one μ2 into 2 μ1, this is going to be 1. Therefore, 2 μ1 equal to 1 μ2. Just check what I got there. And now we are going to comment on this. What will be the comment? Relative refractive index of first medium with respect to the second is reciprocal of refractive index of second medium with respect to the first. Clear? Relative refractive index of first medium with respect to the second is reciprocal of refractive index of second with respect to the first. And this is true for pile of plates also, different refractive indices. Remember, 1 μ2 is reciprocal of 2 μ1, or 2 μ1 is reciprocal of 1 μ2. Very easy. But all these so far we have done in terms of relative refractive index. I told you the absolute refractive index is going to dominate this term, relative one. How? That is going to be more important because all these can be expressed in terms of absolute refractive indices. I am going to take two arbitrary medium here, like this. This is medium 1, this is medium 2. Light coming from medium 1 to medium 2. This medium has absolute refractive index μ1 and this is μ2. What is μ1? What is μ2? That we have done in terms of what? Speed of light. That medium and air was there, then you can define μ1. This medium and air is there, we can define μ2. This μ1 by definition is what? 3 into 10 to the power 8 by C1. And this medium's refractive index mu2 is what? 3 into 10 to the power 8 by C2. Let it be number 1 and this is number 2. Divide 2 by 1. Mu2 by mu1 equal to so what do you get? C1 by C2. Mu2 by mu1, you got C1 by C2. But C1 by C2 what? We have seen earlier. This is 1 mu2. Therefore, 1 mu2 is actually mu2 by mu1. Check my calculation once. Relative refractive index we can express in terms of absolute refractive indices. Okay, done? Now this refraction has many applications. Optical fiber. In your class 9, 10 classes you have seen that refraction can explain the shining of diamond, mirrors, many phenomena. Class 12 the suitable topic is optical fiber. This principle of refraction we can apply in optical fiber. Optical fiber can pipe electromagnetic wave over a long distance. If your transmission of electromagnetic wave which travel in the speed of light is not matter of joke. You will say that why you need to transmit in a bounded medium, in air it can travel. In air of course it can travel, but your purpose will not be solved. Isn't it? The whole beam you will not get. You have to pipe the light through a tube. That is optical fiber. It is a core, it is a cladding. Core means the inner portion. I'll try to draw. It is made of two different medium, the core and the cladding. Okay? Not so big, we are supposed to take small one. I'm just taking one cross-sectional part of it. I mean one small part of it. I've given a rough sketch here, okay? This is a medium. This is a medium whose refractive index is known. Obviously outside is air, you cannot restrict. This is air. This is one medium. This is another medium. Light will enter. Okay? Light may bend. It can, if you draw a normal here, it at this point it can bend towards this, then it can come here, then it can be reflected this manner, reflected this manner. It can travel. Okay? So light can be piped. Refractive index are chosen in such a manner that light will not penetrate the cladding part. This part is called core and this is cladding. Okay? Its refractive index is chosen in such a manner that light after entering suffer reflection only. Refraction of light is banned fully. If refraction takes place, it will go out, the purpose will not be solved. Okay? This is the case of optical fiber, man-made and most useful object. Light can be piped. It is better to say electromagnetic wave can be piped. Signal we can transmit. Many things can be transmitted through the optical fiber. Okay. Now in diffraction we are going to study the change of position of an object due to diffraction. You must have seen that if a coin is immersed in, coin is dropped in a full glass of water, then if you take the view from side, it seems that the glass is raised up. The coin is raised upward. Relative position of the coin is changed. We left it means it should stay at the bottom, but we observe that it is not staying at the bottom. There is a change of apparent position due to refraction. This I am going to explain how object's position can be changed due to refraction. Okay. If object lies in denser medium's refractive index can be related with the position of the object. If it lies in rarer medium, then also it can be done. See how it can be done? I am doing one case, you try the other case at home. So the topic we are going to do now, it is change of position of an object due to refraction. Change of position of an object due to refraction. I am taking this is the medium of separation between two media. And imagine this medium is denser. This medium we are taking, it is a denser medium. Okay. You are situated in a rarer medium. Where are you situated? You are situated in a rarer medium. This is the rarer medium. And this part is what? This is medium of separation I have taken. Separating between two medium. Okay, this is the medium of separation. I have an object situated here and I want to see it from, this is rarer and this one is denser. I want to see the object from this medium, from a rarer medium, but how can I see it? You just imagine the problem. We are sending, my eye is fixed here. My eye is there. If I look at the object directly, can I see it? No. Why? Because due to refraction, path of the light will bend. This is the object. I want to see its image. I have to send 2 rays, you know the concept, or 1 ray at least here. Send a ray here. I am sending this one. Incident here. This is the position of object O, object O. Ray of light incident here. And the normal is like this. this is the normal. Now this light after refraction will go this manner. Okay, going this way it will go this manner. The angle of incidence is I and the angle of refraction is R. How this object's position is changed? I cannot see the painted path, no? I cannot follow the painted path. I have to get the position of image. How can I get? This light I'll produce in backward direction. This I am going to do. What I am going to do? I am going to produce this one in backward direction. Appear to come from this, then image will be formed. So this refracted ray, this is incident ray. This is the refracted ray. Refracted ray produce backward and draw a perpendicular here or send a ray perpendicular. A ray from the object is sent perpendicular. They will meet. If you send this way, it may pass through that. It will pass through. They will meet at a point, and this is going to be the position of image. Clear? This is object. This is image. You understand how image is formed? Clear from the diagram? Clear? Now, so you understand, if you draw a perpendicular here, this is perpendicular. This is object to this point, be M, foot of perpendicular. So real depth equal to OM, real depth of the object, OM. The apparent depth equal to IM. Okay, real depth equal to OM, real depth of the object, and apparent depth of the image is IM. What we are going to prove now, that for nearly normal incidence, mu, the refractive index of this medium, is going to be the ratio between OM and IM. Okay, object situated in denser medium I told you. So this you have to note down. For nearly normal incidence, it can be proved that mu equal to real depth by apparent depth. This we can prove easily. For nearly normal incidence, it can be proved that mu equal to real depth by apparent depth. See how to prove? Nearly normal means what? I and R are small angles. Simple observation. That glass filled with water, I am looking from there, not perpendicularly like this. This is nearly normal incidence. If I am seeing from here, I will see nothing. Okay? So, this let us prove that mu real depth by apparent depth. So, this angle I, this one is R. Vertically opposite. Vertically opposite means this angle, this is R. If this one R, then this angle going to be equal to R. And this one I means this one equal to I. Am I clear? You can follow the diagram. Which one are you understand? This one, this one. You have drawn a perpendicular OM, OIM. Better I draw another diagram here for your convenience. Object is here. Then light incident. This is normal. It will follow bented path. I mean, it moves away from normal. Our eye is situated there. Eye cannot follow the bented path. So we need to produce backward. Draw a perpendicular here or send a ray in this direction. It will come back this manner. All will pass. And this one produced will meet at the point I. This is O and this perpendicular we have drawn. This is our I, this is R. Clear? Which one I, which one R you understand? If this one I, this one I, and if this one, this whole thing R, this one R, means vertically opposite this angle is R. So what I am going to say last few minutes, this angle is also R. A is the point of incidence. This medium has absolute refractive index mu, and assuming my eye is situated in air, this is air, better to say, and mu is the denser medium, that is absolute Ri of this medium. Clear? Now you can write the value of mu easily. What is mu over there? Mu will be here. Mu is equal to sin R by sin I. Why? I is the angle of incidence here, angle of refraction here. I am considering refractive index of this medium. That's why. Not of the second medium where light is going. So mu equal to sin R by sin I. Now sin R is what? R is small angle. So we can replace as R is small angle, sin R can be replaced by what? R, which is nothing but tan R. Similarly, sin I is I, which is nothing but tan I. Am I clear? You can see the diagram. So mu is equal to, what is tan R here? Check. This angle R means this is R. Tan R in this diagram, if you write tan R in the diagram, tan R equal to AM by MI. Tan I in diagram is what? AM by MO. So mu equal to sin R by sin I, which is nothing but tan R by tan I, which is nothing but AM by MI divided by AM by MO. Clear? Hope all of you understand. So this mu now just cancel AM, it is going to be MO by MI. What is MO? MO stands for RD, real depth. Mi stands for what? AD, the apparent depth. Clear? Mi is the apparent depth. So mu is MO by Mi. That mu going to be now real depth by apparent depth. So mu equal to real depth by apparent depth. This is proved. Why we have proved? With in some calculation they say that how much the coin is raised. You tell me no? You tell how much the coin is raised. You said okay, coin and I is the image, so it is raised. But how much? Can you find it in terms of mu and real depth? Of course, that we are going to find. So that term will be referred as upward shift. Upward shift of the object will be what? Let us find in this diagram only. So I am taking the help of this thing only. I am going to define upward shift. Upward shift is y. Y is nothing but OM minus MI. OM minus MI is what? Here we got mu equal to MO by MI. So MI going to be what? MO divided by mu. So upward shift is OM 1 minus 1 by mu. This is called upward shift. Upward shift of the object is OM into 1 minus 1 by mu. Now question for you. If there are piles of plates, object lying below, then what is the effect? How do you find upward shift? Can we find upward shift there? Let me explain the situation. I have certain plate of thickness here. This thickness extend. Then another plate or a medium of thickness, another thickness. This thickness is T1. Above it, we are drawing another one. This one is T2, different medium thickness. How to find net upward shift? So for a pile of plates, we will use superposition. Imagine no plates are there, only one plate. For that, you find the shift that is given by T1 into 1 minus 1 by mu1, refractive index of this medium mu1. This medium T2, its refractive index mu2. T2 1 minus 1 by mu2. Okay? For n plates, it continues. So this thing is nothing but T1 by mu1 then T2 by mu2 Tn by mu n. If you add all these, is sigma Ti by mu I. Okay, just remember this. This way net upward shift can be determined. There is a concept of combined refractive index. You can define it from there. If upward shift remains the same due to a single slit, then that single slit is the replacement of these piles of plates. Okay, just remember this will apply in solving problems. So here we prove that mu equal to real depth by apparent depth, and we have calculated upward shift. If many plates are there, how to find that I have explained. Now my question for you, if we keep an object in rarer medium, then what will happen? Object is kept in rarer medium. This is medium of separation. This is our rarer medium, and this is the denser medium. So this case you are going to solve when the object is situated at the rare medium. When the object is situated at the rare medium, at a point in the rarer medium, then what will happen? Just I am taking the object here. Object, 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 we are taking the object here. Clear? I am not seeing from rarer medium, then I will not see any change. My eyes or a fish is situated in the denser medium. It looks upward. It will see that the object is away from him. I mean image away. That's why. So this is the object. Take a ray. This only you are doing. Take a ray incident here. What will happen to the ray? This is our rarer medium. You need to draw the normal. This is the normal. It will bend towards the normal. Am I correct? It will bend towards the normal. Is that clear? This is your eye. This one R. Point of incidence here. Ray goes this manner. Bent away from the normal. My aim is to get the position of image. How can I get? Real image is not possible here also. I will send a ray. I will send a ray this manner. Either it will retrace the path or it will pass through. You produce it this manner. If it passes through, then this ray you have to produce. This one, this one. Somewhere like this. This is going to be the image. The eye will find, my eye, I told you it is situated here in this medium. My eye will find it at different point. This is away from the object. This time, if this has refractive index mu, we can prove that mu equal to apparent depth by real depth. Clear? This can be proved. Mu equal to apparent depth by real depth. Okay? So, how much it is shifted? That we can find easily. We find apparent depth. Then mu into real depth will be the apparent depth. Apparent depth can be determined. How much it is shifted? You got? Suppose this is the perpendicular here. I want to find this one. How much it moves away? It was there at O, now it is at I. Y equal to Mi minus Mo. Mi is what? This is apparent depth. Mu into real depth minus Mo. Okay? That mu into Mo is real depth only. Mo is real depth. So real depth into mu minus 1. Okay. So this way apparent position of object changes when light goes from one medium to another medium. But in this context, I like to discuss another thing here, that is total internal deflection. What is that? You might have studied before. Total internal deflection. How many of you remember? Total internal deflection. I just remind you, as you have done it before. So I am just telling you which we need for the following classes. Or you take the medium this manner. Just otherwise it will be confused with the rays. I am taking just a medium like this. Sending a ray this manner, what will happen? This ray get refracted. Common refraction. It will be like this. Okay. So incident ray, incident angle and refracted angle, if you see, this is R, this is I. R is greater than I because this is rarer and light going from denser medium. Okay. If you go on increasing the value of I, then what will happen? Value of R also increases. Clear? Now, if you have increased I in such a manner that this is increased, I dashed is more than I, you increase it further. Then we will see that this ray is grazing. This is called it is 90. This angle IC, this IC will be critical angle. So critical angle is the angle of incidence for which the refracted ray makes 90 degree with the normal. And if you say that refractive index of this medium mu, then mu will be sin 90 by mu. Sin 90 by sin IC. 1. So sin IC sin 90 by mu. Okay. So critical angle for which it's happening, that I can find from this relation. If you increase more, then what going to happen? If you have increased more, then light is retained by this medium only. It is not allowing to go. Okay? It will come back to this medium only by obeying the law of reflection. Going this way, this way. This is called total internal deflection. Hope all of you have understood. Okay, this was not a difficult topic.